astronomy seminar. We are very fortunate today to have Dr. Jessica Werk visiting us from UC Santa Cruz. She finished her PhD, I didn't ask you which year, but I know you split it between 2010, split between Michigan and Columbia University before moving to Santa Cruz. We've had a couple postdocs here now, currently a Hubble fellow there. Her work has migrated to a very interesting topic on the circumgalactic medium, a word that everyone should know, or they will within an hour. So without further ado, thank you, Jessica.
Thank you. Thanks for having me. So I'm going to begin with a portrait of a galaxy. So as many of us know and appreciate, a galaxy is not a quiet, uneventful place. Most are born violently and live in a constant state of turbulent complexity and upheaval. A galaxy like the Milky Way maintains a complex ecosystem in which baryons cycle in and out of many different phases, from stars to interstellar medium to dust to the circumgalactic medium. One example of this upheaval is that galaxies drive large-scale winds. These wind-related feedback processes are the dominant mechanism governing the thermal evolution of the galaxy interstellar medium. Galaxies also accrete gas, and this gas accretion is the means by which a galaxy can survive and form stars for several billions of years. Together, winds and accretion are inextricably linked to the physics behind star formation, quenching, and the existence of what I'm going to talk about, the circumgalactic medium. The circumgalactic medium is loosely defined as diffuse gas filling the virial radius of a galaxy bound to the dark matter halo, extending out to 300 kiloparsecs from the galaxy, so about 10 to 20 times the size of the optical disk of the galaxy. Now, this diffuse gas, and I'll go into this in more detail, but one way to think about it is that the interstellar medium, if you might know and love an H2 region with a density of about 100 atoms per centimeter cubed. The circumgalactic medium is about the same temperature, what I'm going to talk about, 10 to the 4 Kelvin, 10,000 degrees Kelvin, but it's 1,000,000 times less dense than a typical H2 region in a galaxy. So keep that in your head. This gas is very, very diffuse. The circumgalactic medium is the place where accreting gas that feeds star formation meets enriched feedback materials. It's where satellites are stripped and disrupted, and it's where the ejecta from galaxies may eventually be recycled. And so I'm going to point out, by way of introduction, that you don't even have to directly observe these phenomena of winds and accretion to know that they must exist, and they must be very important for governing the physical state of galaxies. And so you can actually just know some very global scaling relations of galaxies and infer that these processes must be playing a large role. And the first that I'm going to show here is the universal baryon fraction of galaxies. And so the cosmological baryon fraction of 17% is well known from Big Bang nucleosynthesis and other studies. Yet, galaxies, compared to this cosmological fraction of 17%, appear to be severely baryon depleted. Now, when you look at this as a function of halo mass, the Milky Way is about 10 to the 12, and that's about where this function reaches a maximum, where galaxies contain about 25% of the baryons you expect if they have the cosmological, if indeed the cosmological fraction governs a galaxy halo. Now, that's just looking at the stuff in the disk of the galaxy, but this relation, at least, seems to imply that there's material that flows out of a galaxy, that there's material hanging out around a galaxy. It implies the existence of a circumgalactic medium. Of course, the most basic observation that there are two types of galaxies, red spheroidals that are no longer forming stars and disk-shaped galaxies that are forming stars, cannot be understood without some understanding of gas supply and gas consumption. So recent years have actually brought firm constraints on the growth of the red sequence from a redshift of 2 to present day, which implies, in turn, that many star-forming galaxies are shutting off their star formation, that they're being quenched. And so the means by which this transformation happens from star-forming disk galaxies to red quiescent spheroidals is absolutely related to gas supply and gas consumption. I'll talk more about this as well. You may be familiar with the galaxy mass-metallicity relation. This is often formed the gas phase abundance of a galaxy. It's related to the stellar mass that a galaxy has. It extends over 3 orders of magnitude. It's valid at low redshift, at high redshift, and this universal relationship, this fundamental relationship between the amount of metals, that is, any atoms heavier than hydrogen and helium generated within a galaxy fused in the cores of stars, is intimately related to the stellar mass of the galaxy, but the way in which it's related cannot be understood without invoking both inflows and outflows. I think one of the most recent exciting things to be discovered about galaxies and in their metal content, again, is that all of the metals that galaxies have generated in their lives, and you can do this calculation where you take all the stars a galaxy has, and you can determine its star formation history in the various ways that you do that, and you can figure out how many metals a galaxy should have generated. And then you can count up the metals that you observe in a galaxy, in the interstellar medium, locked in stars and dust, all of these phases that are easily observable. And it turns out that if you only count stars, interstellar medium, and dust within the optical disk of a galaxy, galaxies are missing about 80% of the metals that they've generated over the course of their lives. And so again, this implies that they've lost them somehow. And again, maybe the existence of a circumgalactic medium. Probably one of the oldest arguments for accretion, at least, is the so-called G-Dwarf Problem. And basically, this requires pristine gas accretion. So there's a discrepancy between the observed metallicity distribution in the solar neighborhood than that predicted by what's called the closed box model, where galaxies hang on to all the metals that they generate, and gas stays in this closed box over its lifetime. And so we need gas accretion. The relationship between the surface density of star formation in a galaxy and the surface density of gas in a galaxy is, well known to obey a power law. Again, it extends over many orders of magnitude, over 3 decades in stellar mass. It holds for quiescent disks to star-bursting galaxies. And one of the amazing things about it is that you can actually reconstruct the star formation histories of galaxies, and they're fairly constant over their lives, which implies that the gas fraction hasn't changed, right? But at the current star formation rate of most of these galaxies, they exhaust all of the gas that you observe in them in only 1 billion years to 2 billion years. But most of them we know have been forming stars for 10 billion years. So this requires some infall of new gas. And finally, the evolution of the time of the cosmological mass density of hydrogen in the universe absolutely requires inflows and outflows. And so the value is about a factor of 2 higher at a redshift of 5 than it is in the present day. But then again, if you look at the baryons locked into stars in the present day, it's more than a factor of 2 greater than the amount of gas that they had at previous times. And so it means that galaxies have to be approximately replenished with gas at the same rate at which they're consuming gas over their entire lives. Okay, but of course, these are all global galaxy scaling relations, many of which we know and already appreciate, and we deduce that there must be accretion in winds. But there are direct observations of these processes. Okay, so winds are probably one of the most striking observations. I'm showing you here some images over many different wavelengths. And so our own galaxy, the Milky Way, shown here, is driving a large-scale wind centered on the central, maybe 50 parsecs of the galaxy. And these are giant magnetized outflows traced by these radio lobes from our own galaxy. It's driven by star formation, and it's driving like 10 to the 55 ergs per second into the halo of the Milky Way. M82 is this galaxy here, this galaxy here. It's probably one of the most associated galaxies with winds, and you can see winds exist in warm ionized gas traced by H-alpha emission. They're dusty, they have molecular gas. This is MgC253 traced in molecular gas. We see P Cygni profiles in molecular gas. And then when you look at warm ionized gas along the lines of sites to galaxies, you see commonly that galaxies are driving winds. Most star-forming galaxies are driving some wind, and the rate at which they're ejecting material is usually equivalent to about the rate at which they're forming stars. And you can do these studies observationally. So one of the things about winds is that the wavelength that you're observing, the properties that you derive depend on the wavelength that you're observing. And most of what we see is actually the result of the interaction of main primary wind fluid with an ambient medium of some kind. So again, these might only go out to say 20 or 30 kiloparsecs, and the circumgalactic gas I'm going to talk about is up to 300 kiloparsecs. But at least already some of these observations of winds are signaling that these winds are propagating through some kind of medium. Direct observations of gas accretion are harder to come by, but I'm showing you some of the most relevant evidence for gas accretion, observational evidence. Here is a map of the neutral gas distribution around our Milky Way. The disk is here in this coordinate system, and so you see the Magellan Extreme. This is shown here as well in H1, and this will provide another 10 to the 8 solar masses of fuel within the next several hundred million years to the Milky Way. All of these here are the high velocity clouds in the halo of the galaxy. Many of them we think are accreting. There's evidence when you look at the high velocity clouds in high resolution images, there's this head-tail structure. This is evidence that these clouds are moving through the ambient medium that's hotter and more diffuse. I think probably some of the most direct evidence of accretion are these so-called H1 beards. And this is an H1 rotation curve of the galaxy here. And what you can see here is there's all this gas that's lagging the rotation. And in order to explain this, you have to have some amount of material accreting from the intergalactic medium and then some amount of recycled accretion to explain this lagging gas.
I can think about it before so it's 10 to the 8, so it's about 1 solar mass a year material falling in the Milky Way.
Yeah. Well, the Magellan Extreme hasn't accreted yet. I don't think much of it has accreted yet.
No, I was thinking 10 to the 8 divided by
ultimately,
10 to the 8.
yeah, it's a lot of gas.
On average.
Yeah. So, okay, but what I'm going to talk about is this, again, diffuse circumgalactic gas. And these are observations that we've really only been able to do recently, mostly because the gas is very diffuse, so it can't be traced by its emission directly. We have to do these absorption experiments. And so the idea is that you have a galaxy with a large diffuse medium around it. You use a bright background source, say a quasar, and you point a telescope at the bright background source. The bright background source will show absorption lines, and some of these features you can associate with a particular redshift, right? You're going to find Lyman-Alpha series or Lyman series of absorption, and you'll be able to say this Lyman series of absorption is at a redshift of something very specific, and maybe it's at the same redshift of a galaxy in the foreground. And so then you can associate the material and absorption with the halo of a galaxy. And if you do this, say, 50 to 100 times, then you can start to assemble a sort of statistical picture of what's going on in these furthest outskirts of galaxy halos. So, again, the circumgalactic medium is inflowing material, it's outflowing material, it's disrupted satellite material, it's ambient gas, and it is, maybe an important baryonic component of galaxies that we haven't yet considered. So I'm going to start by just giving you a broad overview of circumgalactic medium, of studies that have been done to characterize this gas. And then I'm going to talk about this one particular survey, which I think is probably, if you're going to try to think about galaxies and their circumgalactic gas, it's the survey to think about in terms of local star-forming galaxies. So, and this is a survey that I've been involved in. I'll talk about some of the most important results. And then I'll talk about how the survey may solve one long-standing mystery, but it might actually create a couple other mysteries that mean we need to think a little bit more about how galaxies are evolving. So, back in 1969, two very well-known famous astronomers hypothesized that all of the absorption lines observed in quasar sources were with multiple absorption redshifts are caused by the gas in the extended halos of normal galaxies. And so this prediction took about 40 years to be borne out with the installation of the cosmic origin spectrograph on the Hubble Space Telescope in 2009. This was the resurfacing mission that we heard so much about. The astronaut Jim Grunsfeld installed this UV spectrograph on the Hubble Space Telescope, and finally we're able to examine this hypothesis and prove that it's true. So one of the things about this diffuse ionized gas in the halos of galaxies is that all of the transitions, all of the important transitions lie in the ultraviolet. And because we are on planet Earth and we like to breathe air and not get radiated by the sun, we have an atmosphere, we can't actually observe these transitions from the ground. We have to go to space. And so this is part of the reason that it took so long to really understand this gas around galaxies. And of course, you could, at high redshift, so for high redshift things, these things could get shifted to the optical wavelengths. But at high redshift, things are a little more complicated. It's harder to associate the gas with galaxies. It's harder to observe the galaxies at high redshift. And galaxies have different virial radii, dark matter properties at high redshift, which means that it's very, very difficult to tell if you're looking at circumgalactic material or intergalactic material at high redshift. So the interpretation is much more complicated. And so at low redshift, you're limited to using the brightest background quasars. And of course, there are a limited number of quasars in the sky. So, like I said, the way that we do these experiments are we take an image where we have a galaxy and we have a quasar. The quasar is at a higher redshift, so it's behind it. The galaxy is nearby in projection. And this quasar then, you know the redshift of the galaxy, you know the redshift of the quasar, and so then you know roughly the distance into the halo that this quasar is probing. So this quasar here is at the redshift of the galaxy, about 75 kiloparsecs into the halo. And so you look down the barrel of the quasar and you see absorption lines. So the way prior to the survey that I'm involved in, that people mostly did these studies because there are so few quasars, is they took spectra of all these quasars, they characterized the absorption in the quasar spectra, they figured out the redshifts that you have these absorption features, and then post facto, they go hunting for the galaxies at those redshifts. And so you can see how that might be, an interesting way to design a survey, but at the same time you might be biasing yourself towards systems with absorption. So you don't know the frequency of absorption. Instead, if you do it a different way, where you just find galaxies and quasars nearby in projection, you know absolutely nothing about the quasar absorption properties, then you go and look at the redshift of the galaxy in the spectrum of the quasar for absorption. You find that yourself doing an absorption blind survey, which may be more interesting in terms of broadly characterizing the gas around normal galaxies. So one of the reasons that characterizing the circumgalactic medium has waited until the late 2009 and beyond is because previous generation spectrographs like STIS, really you could only look at quasars bright with a far ultraviolet magnitude brighter than 17. Now COS is about 100 times more sensitive than STIS. And you can see I tried to draw the distribution of quasars in terms of their far UV magnitudes in the sky, and you can see that most of the high redshift quasars are at fainter magnitudes here. And so finally with COS we're able to get a whole lot more quasars, and you can design these experiments where you have galaxies and quasars nearby in projection that you can have quasars that you can actually observe with UV instruments. And I don't want to bias you that COS halos, the survey that I'm going to talk about, is the only circumgalactic study out there. There are others at high redshift, luminous blue galaxies, ladder break galaxies, quasars paired with quasars. There are luminous red galaxies, but what we're looking at with COS halos is actually normal star-forming galaxies like the Milky Way. You've got a halo mass of say 10 to the 12, a stellar mass of 10 to the 10 or so. And we're just looking at the halos of normal star-forming galaxies, but we also have quiescent red galaxies. So we have red galaxies and blue galaxies all at the mass of the Milky Way. Okay. So just broadly speaking, something we've known for a long time, well not a long time, but since 2009, is that all galaxies from Milky Way luminosity galaxies, L star, down to sub-L-star galaxies, dwarf galaxies, have Lyman-Alpha absorption in their halos out to 300 kiloparsecs. And so I'm going to spend a second talking to you about the axes of these plots. So this is the strength of Lyman-Alpha absorption. This is hydrogen, transition, neutral hydrogen. And so this is in milliangstroms here, so 1,000 angstroms is very strong absorption. You've got the projected separation on the x-axis here from the galaxy. And this is a statistical sample, right? This is one quasar per galaxy. But what you can see here is that at about 300 kiloparsecs, you start to get a lot of upper limits, so non-detections of Lyman-Alpha. But within about 300 kiloparsecs, galaxies of all types are showing Lyman-Alpha absorption. It does seem like it has a declining profile. Somebody have a question? No? Okay. And then you can look at this in terms of a detection rate or a covering fraction. So you see here that 100% of the time, you find Lyman-Alpha absorption out to about 200 kiloparsecs. So at least in terms of hydrogen, these galaxies have hydrogen absorption out to a large distance, usually about their virial radii. The gas actually isn't just hydrogen, it has metals in it. People have looked at this with magnesium-2, which is at around 2,800 angstroms. And so you can actually, this is probably the lowest, the transition that you can look at the lowest possible redshift from the ground. You only have to go to about Z of 0.3 or so to be able to look at magnesium-2. And what you find is that magnesium-2 drops off fairly steeply, but it looks like you've got a high covering fraction or a high incidence of magnesium-2 absorption within about 75 kiloparsecs of a nearby galaxy. So galaxies also, the circumgalactic medium is dusty. This work, I think, is very interesting. This is Rhys Menard's work, who's at Johns Hopkins. And what he did was he looked at 85,000 quasars in the Sloan Tyndall Sky Survey that have redshift greater than 1. And he correlated the brightness of these quasars with the position of 24 million galaxies at redshift of 0.3. And then he measured a cross-correlation between the colors of the background sources and the distribution of those galaxies. And by estimating the colors of these sources, you can get an estimate for the extinction. And when you correlate this with the projected separation here, you find that there's a lot of dust extending out to about a megaparsec around these galaxies. And it turns out that there's as much dust in the halo as there is in the disk of the galaxy. So I think that's a really interesting result. And as far as the warm, hot gas is concerned in X-rays, the detections have been harder to come by, actually. Mike Anderson did some stacking of X-ray ROSAT data, and basically you can really only put upper limits on the amount of gas within 50 kiloparsecs with the X-rays. Some, I think Bogdan in 2013 used XMM Newton to look at the X-ray halo of galaxies, but generally speaking, when you're looking at X-rays, you're really only tracing gas out to about 20 to say 60 kiloparsecs at the absolute most from the disk of galaxies. And when you put the upper limit on the total amount of material in X-rays, it's really not very much. So, so the X-rays have been kind of a puzzle for a while because at least for a Milky Way, the virial temperature of the halo, which is the temperature of the gas that you would expect it to have in a sort of lambda CDM model of the universe, the temperature, the gas at that temperature, about 10 to the 6 to 10 to the 7, appears to not be there. So now I'll talk about the gas at about 10 to the 4 Kelvin and 10 to the 5 Kelvin and try to understand how much of that is there. And so to do that, we use this COS HALO survey, which is an absorption blind survey, right? So galaxy-quasar pairs on the sky. We know nothing about the absorption until we go hunting in the spectrum of the quasar at the redshift of the known galaxy nearby in projection. The galaxies that we're looking at are at a redshift range of 0.1 to 0.3. We're looking at stellar masses with a median right around that of the Milky Way, 10 to the 10.5. At the most massive end, we probe 10 to the 11.5 in stellar mass. We're only tracing the inner circumgalactic medium, so we're going out to about 150 kiloparsecs from the nearby galaxy. You can see here, this is kind of a map of all of our sight lines, where the red squares are red passive elliptical galaxies, and the blue squares are star-forming disk galaxies. And so we get cos spectra of the quasars, which cover important UV transitions in the circumgalactic medium. And we get the high-res spectra to cover magnesium-2, which is this well-known and loved transition. And of course, this work is in collaboration with a lot of people. The PI, Jason Tomlinson, is at Space Telescope, and yeah. All right, so this is just meant to show you the experimental design of cos halos. So what you have here is a galaxy in nearby projection to a quasar. This is 15 kiloparsecs at the redshift of the galaxy. You go looking at the galaxy spectrum, you can get a very precise redshift down to about 20 kilometers per second. Then you go hunting in the quasar spectrum for absorption, and I'm going to show you Lyman-Alpha. And every time, look, you find Lyman-Alpha here. And so you can do this for every single pair. You've got a quasar nearby in projection to a smudgy little thing of a galaxy at redshift 0.2. And you go hunting in the quasar spectrum, and Lyman-Alpha is there. Okay, it's there, it's there. Anyway, I could do this for, say, 50-some sight lines, but that would bore you, so I won't. But instead, just to tell you that this gas is ubiquitous around normal star-forming galaxies of similar mass to the Milky Way. So if you look at the kinematic properties, so how do we know this gas isn't escaping from the halo or isn't just intergalactic medium or something that we're always seeing? So when you look at this and you compile the statistical sample, you can look at the velocity of the gas compared to the galaxy systemic at 0. And here's showing you the escape velocity from the halo. These are various models for what that would be. And what you find is that all of the gas is definitely well within that escape velocity. So this is not gas, this is gas that is bound to the dark matter halo. So like I said, when you look at the H1 properties in bulk, this Lyman-Alpha absorption, we've got the strength of Lyman-Alpha here. I can convert that to a column density, so now this is atoms per centimeter squared. This is a line of sight density of gas. And so what you see here is that strong Lyman-Alpha absorption for almost all of the galaxies that we look at. There are 4 exceptions here, but in general, I think it's actually a pretty surprising result that the red galaxies in our sample, these passive, non-star forming elliptical galaxies that probably don't have much gas to speak of in their disks, have a significant amount of gas extending out to 150 kiloparsecs as seen in Lyman-Alpha. So this is photoionized gas at about 10 to the 4 Kelvin. This is not your hot, shock-heated halo gas. And so, so I'll talk a little bit more about the implications of this, but it's actually fairly surprising. And so what you see here is in column density as well. The red galaxies seem to have almost as much H1 gas, and H1 gas is ubiquitous around these galaxies. The circumgalactic medium, like I said, we trace over a wide range of transitions, and so this is just meant to show you some of the data that we have. We have various ionization states of adjacent metal lines. So we've got carbon 2, we've got carbon 3, silicon 2, silicon 3, and this will become important for one particular study in determining the ionization fraction of the gas, how much of the gas is actually ionized. And we also have oxygen 6. And so oxygen 6 is kind of weird. Oxygen 6 doesn't really exist with photoionized gas in abundance, but yet we find it in abundance, and I'll show you that result. So, so we think oxygen 6 might be in a slightly different phase of gas. But you can see here, what's interesting about oxygen 6 is that the absorption tends to happen around the same velocity range as the lower ionization state gas. Its shape tends to be a little bit broader, and sometimes it's very different, and sometimes it looks about the same. So if you look at the oxygen 6 for this galaxy, for instance, it's almost completely different. I think I was showing it on the previous slide from where the low ionization state gas is. This is silicon 2 and silicon 3 in red and black. It's basically the same in this one. The silicon 2, silicon 3, and oxygen 6 all have the same velocity structure. And so it's kind of a mixed bag. But generally, we think the oxygen 6 is probably a little bit different. It's probably a little bit hotter, 10 to the 5.5 Kelvin, than the cooler gas, and it might be ionized by a totally different process. And one of the things...
You're talking about this, I mean, is that part of this warm, hot, intergalactic medium that Kendall suspects?
Maybe, probably not, actually. And so I will talk about this, but it's bound just the same way as the rest of the gas, and like statistically, the level of absorption, the column density of the oxygen, oh, this isn't oxygen 6 yet, but the column density of the oxygen 6 is much higher in the circumgalactic gas than it is at this sort of like randomly distributed, sight lines that aren't necessarily associated with galaxies. So this is halo gas.
Okay.
And I'll show you some more.
But it has to be at higher temperature.
It has to be at higher
10 to the
temperature.
4 stuff.
10 to the 5, yeah. 10 to the 5 and a half or so, we think. Although it doesn't necessarily have to be. I'll talk a little bit about that too. So, okay, so the lower ionization state metals, like I said, we trace silicon-2 and silicon-3. We have about a 70% covering fraction for metals within 150 kiloparsecs and 90% for the higher ionization state gas. And so what you can get from this plot is that there's not really a difference between red and blue galaxies. Fine. We saw that with the H1. It's all photoionized gas. So there's cool gas around these galaxies. It's metal enriched for all of them. But I think what's interesting about this is that the detection rate in the higher ionization state, silicon-3 versus silicon-2, it's always higher. So this is telling you something already about the ionization state of the gas, and just that the bulk of the gas is ionized rather than neutral. So now we can look at oxygen 6. And so oxygen 6 is weird because there is actually a difference between the red and the blue galaxies as seen in the oxygen 6. So this is the hotter gas that I was telling you about. And it looks like the dichotomy in red and blue galaxies tends to be traced by oxygen 6, where red galaxies don't show very much oxygen 6 in their halos, and blue galaxies invariably show oxygen 6 in their halos. And it's much stronger. I mean, even if you do take that there are 4 detections here, the blue absorption is considerably stronger for oxygen 6 than the red galaxy. So oxygen 6 tends to be associated with ongoing star formation in the galaxy. And I'll come back to that in terms of a discussion about quenching, how galaxies shut off their star formation and how the halo properties of the gas reflect that. But oxygen 6 is a very interesting clue. And I will say that this discovery here is also counter to expectations. So if we thought that we were going to see a dichotomy in terms of red and blue galaxy properties, we would have thought that the red galaxies didn't have H1 and had oxygen 6, rather than what happened, what vice versa is what we ended up seeing. So we've been trying to understand this result, and I'll talk about how in a minute. But first, I want to talk about the galaxy halo missing baryon problem. And so I've just shown you empirically what we see when we look at halos of galaxies. There's a lot of gas there, but how much gas we need to quantify. So we can actually do this. And so like I told you in the introduction, that relative to the cosmological fraction of baryon fraction of 17%, the universal cosmological baryon fraction, galaxy dark matter halos are missing about 60 to 75% of their baryons if you consider the gas and the stars in the disk alone, and also if you include the X-rays, which really provide something negligible. And so this has led some people to think that maybe galaxies just don't have their cosmological fraction, of baryons. Maybe galaxies just are baryon poor, and all of the baryons in the universe are just in this warm, hot intergalactic medium, this WIM, that people are constantly shoving baryons into. There's a universal missing baryon problem, which almost certainly is solved by an intergalactic medium, or WIM, which we have never observed directly, I will say. There are some tantalizing suggestions of the existence of a WIM observationally, but yeah, so okay, one option is that galaxies just don't have their fair share of baryons. And the other option is that they're in the halo. And previous studies have focused on hot gas in the halo, because the virial temperature of a Milky Way size halo should be about 10 to the 6 to 10 to the 7, and that's where you would expect to see your X-rays. But the X-rays, they're not there. You don't see gas at that temperature. But what about this cool gas that we see a lot of? How much gas? Does this help solve this problem? Are the missing baryons in the cool gas around galaxies? And so in order to determine this, like I said, you need to understand how much of the gas is ionized. So basically what happens is you've got all of the gas is mostly hydrogen, right? In the universe, all of the gas is mostly hydrogen. And so all these metal ions that we're observing represent a small fraction of the total amount of gas. So if you're going to try to understand it, you want to understand the hydrogen. But the hydrogen, like I said, the bulk of it's going to be ionized. And sadly, there are no transitions in absorption that probe ionized hydrogen. All we see is neutral hydrogen. But that's a very, very small fraction of the gas. And so in order to perform this ionization correction to find out how much gas is ionized, we have to do photoionization modeling. But to do that, what we can say is silicon 2 and silicon 3 are associated with this gas, this ionized hydrogen, and the neutral hydrogen is sort of the tip of the iceberg of the hydrogen. And so you can get an ionization correction using the adjacent ionization states of these metal lines. So silicon 3 to silicon 2, carbon 3 to carbon 2, you plug that into a photoionization model where what happens is you assume the gas is in thermal and ionization equilibrium, that it's being ionized by some radiation field, okay? And you can do a number of radiation fields, but the one that does the most is the extragalactic ultraviolet background, EUVB is what it's called. And people have been trying to quantify this for many years. We use one that's typically used called the Hart-Maddow extragalactic UV background. But you can also include ionizing photons from the galaxy itself. It turns out that those don't matter that much. You can alter your spectrum as much as you want to try to understand how much that impacts the analysis. But the very sort of vanilla way to do it is to just model it as being photoionized by an extragalactic UV background. That's a simple conservative way to get the ionization fraction of the gas. Okay? And so when I talk about the ionization corrections that I'm applying, I'm actually doing it in the most conservative way possible. Most of the gas that we observe in H1, the absorption lines are saturated, right? So there's probably more there, it's just our signal to noise isn't high enough, and so that gives you a lower limit on the total column density of neutral gas. I take those lower limits of neutral gas and I apply the ionization corrections to the lower limits of neutral gas. Now, again, those could be an order of magnitude off. There could be an order of magnitude more neutral gas, which would raise these mass estimates by an order of magnitude. So everything I'm going to tell you about the total mass of material in the circumgalactic medium, everything I'm doing right now is the conservative approach. So the number I'm going to get is going to be, the lowest possible value in this cool gas. So what you do is you take this grid of outputs from your cloudy models that give you a solution for the gas, and you compare that with what you actually observe to get this ionization parameter. The ionization parameter is just the flux of ionizing photons divided by your gas density times the speed of light. It's this dimensionless parameter, but it's basically going to tell you what fraction of the gas is ionized. And so here on the y-axis here, I'm showing the column density outputs, and these are cloudy models. So at various ionization parameter, cloudy, this photoionization modeling system, predicts that the following distribution of ionization parameters for different species. And so we observe these different species, column densities, and what you find here is you can compare this with the cloudy model. So these bold parts are the observations. Sometimes we have lower limits, sometimes we have upper limits, but these also all come in handy. And so you compare this whole suite of absorption line measurements with the cloudy outputs. You do this for every single one of them, for the ones that actually have ionized metals in their halos, and you can get this ionization correction. So this is a distribution of ionization parameters with the virial radius now. This is the impact parameter. The projected radius from the galaxy is just now parameterized with the virial radius. And you can see, maybe there's a trend, but that's not really the point of this plot. It's just to show you that the ionization parameters are typically around -2.5 or so. And there's a broad range there. There's a lot of uncertainties in photoionization modeling. But like I said, I'm taking the most conservative approach, okay? I'm going to show you what are lower limits.
Maybe that's the answer to the question I was asked, which do you see any evidence then for multiple phases?
Yes, actually. Oh, that was one thing that
Right,
I'm supposed to point out here is that oxygen-6 is not photoionized.
Mm-hmm.
There's no way. There's just too much oxygen-6 that we observe to be consistent. Like, we would have to observe, several orders of magnitude less oxygen-6 than we do for it to be consistent with being photoionized by an extragalactic UV background.
Okay.
Now, there are other ways that you can photoionize oxygen-6, but it has to be in a totally separate phase most of the time.
What does Ramil say? I'm just curious to know what Ramil's play would say. But do you jump up and down and say it's the wind or not? That's where
No. I don't think he thinks that it's the wind at all. I think that he just thinks it's a different process ionizing. Like I talked to Ben Oppenheimer a lot,
Yeah.
and so there are different ways. You can photoionize oxygen-6 just fine if you change your ionization parameter, right? So the solution for ionization, it would just mean that oxygen-6, is not all of the gas, and your ionization correction ends up being really huge. But I'll talk actually a little bit more about oxygen-6 and how it's ionized. So, so what you can do now is apply this. So what you take is a total hydrogen column. Now not an H1 column density, but a total hydrogen column density distribution as a function of radial velocity using these conservative values. Again, these are lower limits, most of them. So you see these arrows pointing up. This is where the H1 Lyman-Alpha line is saturated. And so what you can do is when you have a column density distribution, which is atoms per centimeter squared, you can get a total mass by assuming that these things are mapping, say one halo now. We're just grouping it all together, all galaxies of this mass, of this redshift. And you can get a calculated mass by assuming that it's like a surface density, right? And so you just integrate it. And so I'm going to show you the results for the total mass. I'm going to show you the very, very lowermost limits on the amount of gas in the halo. And then I'm going to show you a more optimistic, sort of preferred estimate. This just is like an ionization parameter in the middle. That's still probably a low ball of it, okay? So again, this is just showing you the missing baryon problem. The disk, it really gives you anywhere between 15 and say 25% of the total baryons. The hot CGM is X-rays, it's not much. And so now let's add in the cool CGM and the warm hot CGM, which is oxygen-6, and get a total here. This comes from something totally different, but it's not as big. But the cool CGM, you can see, already is going to be more than the disk itself in the lowest limit estimate. And in the optimistic estimate, the cool CGM gives you about 50% of the total baryons. So already we're almost there. You can see if you add up all of these components, instead of missing baryons, galaxies may indeed have all of their baryons relative to the cosmological fraction. And these baryons, instead of being in hot gas, are in 10 to the 4 Kelvin photoionized gas.
So this plot is showing in the solid is this conservative estimate, and then the hashed is the...
That's like a preferred estimate. When you do the corrections, it's still to the lower limits of hydrogen, but you just take the middle ionization parameter. Like there's some slop in the ionization parameters, and so you just take a preferred estimate rather than the lowest possible
But you're a substantial
ionized gas
fraction of the way
fraction.
there, even if you're very conservative.
Exactly. Even if you're very conservative, you're still doing a lot better than you were previously.
We still require a non-insignificant fraction because it's warm hot. Yeah.
That's right. But there's a ton of oxygen-6 out there. Yeah, we can talk more about the oxygen. I'm going to talk more about the oxygen-6 actually, because it's an interesting puzzle. So great, galaxies might have all of their baryons. So what does this mean in terms of the metals? So instead of looking at just the surface density of hydrogen, you can make a plot in terms of the surface density of oxygen now, using these lower ionization state lines, assuming that the silicon relative to oxygen is the same in these galaxies as it is in the Milky Way or the Sun, which, non-solar abundance ratios happen, but not by more than a factor of, say, 2 to 5. So we allow for that swap. These error bars include non-solar abundance ratios. So the metal surface densities apply about 10 to the 8 solar masses of oxygen in the halos of these normal star-forming galaxies. And so previously, people might have said, well, wait a minute, how are all those metals out there? There are no stars forming out there. How do you get the metals out there? That's preposterous, because that's the total amount of metals, that's more than the total amount of metals in the disk itself of a normal L-star galaxy. But, as I showed you before, when you consider only the disk, the interstellar medium and the stars and the dust and the disk of the galaxy, galaxies are missing 80% of their metals. So now let's add in the circumgalactic medium in terms of oxygen and the lower ionization state gas that I spoke about, and it looks like you can get almost all the way there. So this 10 galaxies are missing about 10 to the 8 solar masses of oxygen from their disks, and we find about 10 to the 8 solar masses of oxygen in the halo. So this is no longer a problem. It's no longer a problem of missing metals. It turns out that galaxies tend to retain most of the metals that they generate in their disk. It's just not in the disk of the galaxy itself. And so this is showing you here that most galaxies, most normal star-forming galaxies, are driving winds. And I told you this earlier in the introduction, that the rate at which they're expelling material is approximately equal to the rate at which they're forming stars. So say you have a star formation rate of 1 solar mass per year, you're also ejecting gas at about a rate of 1 solar mass per year. And Kate Rubin published this study where she looks down the barrel of galaxies. You find a component of absorption down the barrel of galaxies in magnesium-2 that's associated with the interstellar medium. But then there's a blue-shifted component of that gas that's quite significant. And by measuring that blue-shifted component's equivalent width, you can find that a ton of material is not consistent with being associated, but it's instead moving toward us at velocities of, say, 200 to 500 kilometers per second. This isn't enough to escape the halo, but it can certainly put a lot of material in the halo over, say, 1 billion years. And so everything is shaping up to be a nice, rosy picture where galaxies have all the baryons that they're supposed to, where they hang on to all the metals that they've generated over their lives. They're driving these winds, and so maybe this picture makes sense. So now I'm going to tell you a couple things that don't seem to make sense with these results. And so one fundamental thing about galaxies is that we think that they quench. They shut off their star formation at some point. And so I think looking at circumgalactic gas around galaxies that could be accreting onto galaxies, that could have come from the galaxies, this circumgalactic material is inextricably linked to the physics behind this quenching process. So if it's a lack of cooled gas flows from the intergalactic medium that terminates star formation in galaxies, then the circumgalactic medium would presumably reflect this. If the interstellar material of quiescent galaxies is rapidly ejected by, say, some AGN, then the circumgalactic medium would reflect this. And if there's some mechanism keeping galaxies dead, keeping gas from falling onto galaxies, then the circumgalactic medium might reflect this. So let's just review some of the processes, the most common ways that people think galaxies are quenched. So the top two are what people talk most about. The halo quenching model is that galaxies build up enough stellar mass and they reach a transition mass of about 10 to the 12. This is about the Milky Way halo, is about at the transition mass, where now cool gas that's accreting onto the galaxy immediately shock heats when it gets to the halo. And so there's no more cool gas accretion. All of the gas is hot, so there's no fuel there. And one of the other ways is black hole feedback, basically. Quasar mode and radio mode can expel a lot of material. It turns out that it's really efficient at expelling material. When you do simulations of this, it's almost too efficient at expelling material. But the main point is that most models of quenching and quiescence are tuned to either keep gas from falling onto galaxies or make a lot of gas go out of galaxies, right? Galaxies are no longer accreting enough gas to keep forming stars. So the way to look at this problem is then you might want to follow the gas. People look at gas inside of quenched galaxies. There's some passive galaxies have molecular gas and H1 gas. It's not as much as their star-forming counterparts, but this is related to quenching. But there's also gas outside of quenched galaxies. And so this is what we spoke about before, where when you look at the cool photoionized gas in terms of Lyman-Alpha or even the metals, the red galaxies are not that different from the blue galaxies. You wouldn't necessarily expect to find all of this cool gas outside of red galaxies because there's what's to say that this gas is available, it's there, it's near the galaxy. And the cooling times are such that it should cool and fall onto a galaxy. So you might say, okay, well, you have kind of a small sample here. Maybe these red galaxies, maybe you're not associating with the red galaxy. There's some other galaxy at exactly that redshift, some star-forming galaxy, and you haven't seen it or something. I mean, it would be weird, at that level. But also, this is seen for luminous red galaxies. So Guangzhou Zhu at Johns Hopkins has done a stacking experiment with magnesium-2 around luminous red galaxies in SDSS, and you find a ton of cold gas as traced by magnesium-2 around luminous red galaxies. And now Cos Halos isn't on here, but the magnesium-2 around cos-halos galaxies would be right around here, and the luminous red galaxies have more cool gas that's traced by magnesium-2 than normal star-forming galaxies. Okay, so it's not a small sample effect. It's probably not group. And it's directly at odds with theoretical predictions. And so I'm just showing you here work by Kyle Stewart, who actually predicted a covering fraction of H1 gas. And at the halo masses that we're looking at here, they predict that there's a very, very distinct drop in this covering fraction. And in fact, the covering fraction is really only about 60%, maximum of 80%, and then it just drops. And where we're looking is out here. We find a covering fraction of 90%, so off of this plot, which is just very inconsistent with what models of quenching predict.
And that's for halo mass quenching. That would be the prediction for.
That's the
sort of
prediction for
shock
standard, halo mass quenching, yeah. And that's really the only one that I was able to find to compare it with. So now, I said that H1 doesn't reflect the dichotomy, but the oxygen-6 does. And so around red galaxies, oxygen-6 is mostly missing, and around star-forming galaxies, it's present in great abundance. And in fact, there appears to be a correlation with the current star formation rate of a galaxy and the abundance of oxygen-6 in its halo. And so you might not necessarily expect that. I mean, at 200 kilometers per second, when maybe if the gas is moving at that rate from a galaxy, the gas that the star formation is driving out there, and going out to 100 kiloparsecs into the halo takes billions of years. So why would the present day star formation rate of a galaxy be associated with the amount of oxygen-6 in the halo? It's a very strange result, but let's take it as a marker of the quenching process. And so we've been talking a little bit about oxygen-6 and how it might be different from these lower ionization state lines that we're looking at. And so one of the questions that I've been exploring, and this is brand new work, are the physical conditions that give rise to oxygen-6. And so how does it coexist with cool gas, and why is it absent around quenched galaxies? And so one of the clues to answering this question lies, I think, in nitrogen-5. And the fact that we never see it, not around star-forming galaxies, not around quiescent galaxies. It's a strong transition. We see nitrogen-2 and nitrogen-3 in the cool photoionized phase, but we never see nitrogen-5. The ionization potential of nitrogen-5 is a little bit lower than oxygen-6, but you would expect it to be around the same temperature as oxygen-6. It's a similar ionization potential energy, and yet it's not there. And so you can look at this in terms of stacks. You can stack the cos-halos data, nitrogen-2, nitrogen-3, silicon-3, and there's even silicon-4, but there's no nitrogen-5, and then there's a ton of oxygen-6. And so this absence of nitrogen-5 is actually fairly constraining in terms of what's ionizing the oxygen-6. I'm going to skip this plot. Basically, all right, I'm going to walk you through this really quickly. And so these are the ratios here of nitrogen-5 to oxygen-6. And these are ratios of silicon-4 to oxygen-6. Silicon-4 also has a fairly high ionization potential energy, and so you might expect if there's too much of it to be explained by pure photoionization, much like oxygen-6. And so you can take these ratios, and a lot of them are limits, that's fine, but what you see here is that pure photoionization by an extragalactic UV background doesn't really get you there. Even an ionization, this is a huge ionization correction of -1. That implies, a megaparsec size scale for the oxygen-6, it doesn't get you there. Now, collisional ionization, which is the other process that people use to create oxygen-6, really only works for a very specific temperature, about 10 to the 5.4 Kelvin, but at that temperature, you make no extra silicon-4 to speak of. And so it really isn't helping you much there. And so what we've done is we've done this analysis, and we rule out some of the most popular ways to ionize oxygen-6, and there are two things that remain, okay? One of them is this orange line here, and so this is how you can make oxygen-6 one way, is that you, in addition to an extragalactic UV background ionizing your gas, you have ionizing radiation from the galaxy. This isn't your typical ionizing radiation from a galaxy, from say a starburst 99 spectrum, and then some escape fraction of ionizing photons. It actually incorporates this extra component. And the extra component has to be at about 10 Rydberg, and it has to be strong. And some people think one way to get there, and Sebastiano Cantalupo has done some of this work, where high mass X-ray binaries in the disk of the galaxy produce this sort of soft X-ray component to the galaxy SED, and this escaping ionizing radiation comes in from the galaxy. This is why it would be associated with the star formation, the fraction of high mass X-ray binaries, and you get a significant amount of oxygen 6 and no nitrogen 5, and you get enough silicon. Well, we don't know. I don't think that anybody's really observed that. But all this is saying is that one way to do it is if there is, and you can actually constrain the amount of flux that there would have to be at 10 Rydberg to make this work, and it's a lot. It's something like 30 times greater than what's provided at 10 Rydberg by the extragalactic UV background. And so that's one way to do it, to make oxygen 6. In that case, the oxygen 6 is photoionized. Its temperature is around 10 to the 4.5 Kelvin.
But by this extra spectrum.
But by this extra soft X-ray component to the SED. Okay, so the other way to do it, and then there are all these complicated non-equilibrium models, like shock ionization, turbulent mixing layers, which is Kelvin-Helmholtz instabilities, and this boundary layer of cool gas with moving within a hot medium. There's conductive interfaces where you've got gas condensing from the hot gas and gas evaporating from the cool gas and mixing in this kind of, again, this interface layer of the gas particles. But none of these work for the column densities of oxygen 6 that we observe and the ratios of nitrogen 5 to oxygen 6 that we observe. The only one that remains from these weirdo non-equilibrium models is this radiative cooling flow model. And so what this is it's a gas flow moving within the halo of a galaxy. It's either maybe accreting, it's moving out of the galaxy, and there's collisional ionization going on in this gas, and then the hot upstream component is sort of self-photoionizing this other component of the gas and producing the gas in just the right ratios. The column densities are a bit of the question as to whether or not they match. This hasn't really been done for any other galaxy other than the Milky Way, but the Milky Way has this distinct geometry. So you could be, say, looking along a flow. So it's unclear how the column densities compare, but it's really the only one right now that seems to remain. And so basically, the two remaining mechanisms for oxygen 6 give you a hint at this dichotomy where you've got either star formation producing oxygen 6 from this extra soft X-ray component, or you've got oxygen 6 signaling this cooling flow, this gas accretion onto galaxies. And the fact that you don't see it around passive galaxies means passive galaxies are not accreting their gas. For some reason, the gas is hanging out up there, and the oxygen 6 is just kind of a marker of this lack of accretion around passive galaxies.
Why can't it just be outflows from star-forming regions?
So I think that's kind of this. So the outflows from star-forming regions we think are mostly at a lower temperature range, around 10. The bulk of the material is about 10 to the 4 Kelvin at this sort of warm photoionized phase. But if you have this extra component that's sort of heating this oxygen 6, then maybe, yeah, you can get there in that way.
Do you see O6 in H2 regions?
That's a good question. I mean, you see oxygen 6 in the Milky Way. I don't know if it's associated with star-forming regions, though. I don't know.
It's really hot.
Yeah.
It's like 10 to the 5th.
Okay, and so in the last 2 minutes, I'm just going to tell you another thing that is really bothersome, and this is pressure equilibrium, right? So you need pressure equilibrium for anything to really exist. Otherwise, it'll evaporate immediately. So these cool gas clouds, you would assume that they're in pressure equilibrium with some hotter gas at the virial temperature, which hasn't been observed. It's super diffuse, but it hasn't been observed. But what you can do is you can predict what the hot gas is doing, just from a simple Navarro-Franklin-White distribution, adiabatically evolve it, and then predict these cool clouds, cool pressure-supported clouds condensing out of a hot medium. If we're going to observe the gas at all, it has to be hanging out for a billion years or more around these galaxies. We know the time scales for ejecting the material. It has to have a long enough lifetime so that it doesn't just evaporate immediately or cool immediately. The time scales are such that you have to require pressure equilibrium. So do we see pressure equilibrium? Well, we can get a density. It's just basically the reciprocal of the ionization parameter. This comes out of the photoionization modeling where you get now of gas volume density of hydrogen, the gas densities are low. Remember I told you it's about 1 million times less dense than a typical star-forming region. And so you get about 10 to the minus 3.5 or so as your average gas density. And so you can use these predicted density profiles for the hot gas, and it turns out that the cool gas lies on this predicted density profile for the hot gas, which would mean that pressure equilibrium, not so much. It's off by several orders of magnitude. These cool gas clouds should have a density of about 10 to the minus 1, which is a full 2 orders of magnitude higher than what we see it to be. So this simple picture of a halo where gas is surviving for long time scales in the halo because it's pressure supported by a hot medium doesn't work. All right. So maybe, I don't know. Well, there are several solutions, but I'm gonna leave you with a summary since I'm now at time. And thank you.
Great, thanks. More questions, Jessica?
So two kind of, I guess, unrelated questions, but so if I could just ask, I'm not exactly familiar with the sort of terminology here, but 06, what does that exactly correspond to with the energy levels of oxygen?
Yeah, so I think it's about 10 Rydberg in terms of its ionization potential energy, which is like 110 electron volts, 120 electron volts, 130, 136.
This is the valence electron undergoing transition, correct?
You what?
This would be one of the valence electrons.
That's right.
Okay. And when you say it might have different phases, what do you mean by that? Is that just the different temperatures?
Different temperature, different density, yeah.
Okay.
Yeah,
Okay.
gas, so yeah, just gas at a different density or temperature.
How did you make so that's one.
Uh-huh.
How did you make the diagrams? Yeah.
So I did that on my iPad using an app called Paper. It's a nice little app. You can use your iPad, like just drawing. It has little tools.
Oh,
Draw
okay.
with a stylus or your finger. Yeah, it's pretty cool. This is the first time I've ever done that too. I thought it would be a fun way to use my iPad.
Right.
So what can you say about the geometry or the kinematics of the gas? Like, I mean, is it just in streams that's like sort of orbiting, or is it more diffuse? Or?
Yeah. So it's probably more diffuse. If it were just in like cold streams, for instance, at least like the simulations that predict the cold stream covering fraction of gas, it's super low. It's like 20% or something. And we find like 100% covering fraction for gas around normal galaxies. So it's got to be diffuse. What I picture, which might be wrong, but what I picture is a lot of clouds along any given line of sight. So you've got your galaxy and you've just got clouds. And it's not necessarily volume filling because you've got a huge volume, but you've got at least like 2 or 3 clouds along any given line of sight through the circumgalactic medium. But they're fairly, spaced out clouds. And one thing, you said geometry. So hold on, I'll show you something. It was a hidden slide, but I'll show you now. So you can look at this in terms of the inclination of angle of the galaxy. And I've just been doing this lately. You have to do AO imaging because the galaxy images are really bad and slow. But you can look at it in terms of how it's oriented along the disk and along the pole. And it looks like, at least, that the oxygen-6 follows the low ions and that it's like more abundant along the pole of a galaxy, which tends to tell you that it's maybe part of some biconical, outflow. So maybe there's more gas.
So you would do it with oxygen 6?
No, I can do it with all the, I have
Okay,
lots
okay.
of magnesium too and stuff too.
With all the different.
Yeah. Oh, the magnesium too is actually way more associated with the pole. Oxygen 6/10 is a little more diffuse.
What about Lyman-Alpha?
Lyman-Alpha is similar to the oxygen 6.
But would this actually go along with the idea that it's being heated somehow by the processes of the disk? Oxygen 6.
That at least like the gas is more, probably that it's just part of some sort of like recycled, accretion mechanism where you've got stuff coming out and then it's coming back down. Yeah.
did you see this sort of thing in the intercluster medium?
So that's a good question. There hasn't been much done on the intercluster medium. The Virgo cluster has had it done, and it turns out that when you just look at plain old cluster gas that's kind of far from galaxies, so you're not looking at circumgalactic gas, first of all, circumgalactic gas is more likely to be stripped in a cluster. And second of all, the intracluster medium has column densities of Lyman-Alpha that are a lot lower than typical CGM of an isolated, say, L-star galaxy. So the intercluster medium is probably a more violent place, and gas is a lot hotter. And actually, that's one place when you look at the intercluster medium in hot gas, you can find all of the baryons of a cluster in the hot gas. So clusters have some other processes going on that keep the gas hot.
But that warm area is really hard to study. Yeah.
Yes.
Whether it just doesn't show up.
Absolutely.
So I kind of had a question about that. That plot that showed the baryon fraction with your most conservative estimates.
Yeah.
So you had mentioned this kind of preferred result from kind of picking out from the grid on your photoionization simulation. It seems like there's a lot of wiggle room there. Where do you go on that, taking that forward? How do you, the discrepancy between the solid and hash? How do you?
That's a great question. One way to do it is to shore up the H1 column densities. So like I said, a lot of them are saturated. We actually got a program approved to go back and hit the full Lyman series. So Lyman-Alpha is saturated, but you can go down a Lyman series and get weaker transitions. So we have a program that does just that. And so right now we're getting good, well-constrained column densities in the H1, and a lot of that uncertainty goes away when you get better H1 column densities. Now, the systematic uncertainties in the photoionization modeling, including the spectrum of the photoionizing radiation, I mean, all of these things, that will be done in some other way. So these uncertainties people take by compiling, loads and loads of quasar spectra over millions of redshifts and over many different redshifts. And so that's being done too. And so once we get better constraints on that spectrum and better constraints on the H1 measurements, then I think we'll have this hashed area tighten up.
Okay, so those sorts of getting at that saturation, that's helping you in the warm hot.
No, unfortunately, the oxygen 6 isn't tied with the nitrogen.
Yeah.
You don't know how much hydrogen is there for the oxygen 6. You can get metallicities if you have good H1 measurements for the cool gas and assume that it's the same metallicity as the oxygen 6. And if the oxygen 6 is at the same metallicity, then you can make some assumption about what the hydrogen is doing.
Because that's the box that I found really curious.
Yeah, that is the box that everyone finds curious, and unfortunately there's not much we can do until we understand, first of all, what's ionizing oxygen 6, which is hard, but we can place constraints on it. And second of all, how much hydrogen, what the metallicity of that gas is. We don't know.
All right, we are over time. Before we thank her again, there is grad student harassment at what time? 2:30. Okay, so I think plan on that. Otherwise, she's around all day. If you would like to meet with her, let me know. We'll try to squeeze you in somehow. Otherwise, thank her again.